Now that we've got an inner product to measure length, we can talk about angles and orthogonality in an inner product space. So we'll talk about finding the angles between vectors, we'll generalize the Pythagorean theorem, and then we'll talk about orthogonal complements of a subspace. So back in chapter 3, when we had learned about the dot product, we were able to use that to find the angle between two vectors was u dot product v over the magnitude of u magnitude of v. Okay, and then we either found our angle in radians or degrees. Now we're going to take and generalize this for any inner product space. So the cosine of theta is equal to, instead of the dot product, we'll use the inner product of vector u with vector v, and we'll still keep the magnitude of u and the magnitude of v down here, remembering that the magnitude of u or v vector is simply the square root of u inner product with himself, which is okay because by our fourth axiom, this has to be greater than or equal to 0. So let's look at our first example here. Let's take P2 polynomials of degree 2 under standard operations, and let's use our inner product that we learned last time, namely basically the dot product. And we showed that this was an inner product space. I want you to find the angle between f vector being the function x and g vector being x squared plus 1, and then sketch a graph of f and g indicating the angle between them. Let's do this one together. So if we do this, f vector inner product g vector would be, let me just show this, so 0x squared plus 0x, plus 1x plus 0, inner product with 1x squared plus 0x plus 1, and that's going to be 0 times 1 plus 1 times 0 plus 0 times 1, which is a whole lot of nothing. So that tells me that the cosine of theta is going to be 0 over, well, it doesn't matter what these guys are, but they'll be magnitude of 1 for this guy, and 1 squared plus 1 squared is 2 square root of 2. So 0 over square root of 2 is still 0, and therefore cosine of theta being 0 means that theta must have been pi halves radians, aka 90 degrees. Now, here's where things get a little bit different, because this is not just our arrow vector space. If we were to graph y equals x, and then y equals x squared plus 1, let's do those in different colors here. You can see that those actually never meet. And we're saying that in this inner product space, there's an angle of 90 degrees between them, but I don't see any 90-degree angles between these guys. So when we talk about the angle between the vector, it's not quite as easy to see or understand in a non-arrow vector space like this. Let's go ahead and have you try number 2 here. We'll play with a different vector space, in this case M22, matrices that are 2 by 2 with real entries and standard operations. And we'll use the inner product we showed last time of U transpose V, take the trace of that. So find the angle between these two vectors. I'll give you a minute to try that on your own, and then we'll come back and see how you did. Okay, so I did U inner product V and got 12. Magnitude of U is square root of 30. Magnitude of V is 3. So if we take a look at our generalization for the inner product, finding the angle between vectors, we get this guy. And using my calculator, I find out that theta is 43.09 degrees, or 0.752 radians. All right. So in chapter 3, what did orthogonal mean? Well, orthogonal meant for arrow vectors, it was right angle or perpendicular. But we saw that this got a little bit harder to tell when we got into R4 and other vector spaces. And we see here that if we've got a pair of orthogonal vectors here, their inner product is 0, then it's hard to see where the 90-degree angle is. We can't really see it. But in his space, there is a 90-degree angle. So what I want you to do now is find a vector h in P2, polynomials of degree at most 2, that is orthogonal to both f and g from number 1 above. And we'll find a non-trivial vector w in M22 that's a 2 by 2 matrix that's orthogonal to, let's just say, the U matrix here. So we'll give you a minute to try those and see what you come up with. So here's some work I did. Remembering that P2 behaves like R3 does, we can think of this F vector as the 0, 1, 0 vector, the G vector as 1, 0, 1, and we saw something pretty cool in chapter 3 that gave us something that was orthogonal to 2 input vectors in R3, and that was the cross product. So I did a quick cross product here, finding out that it'll be I plus 0j minus k, corresponding to the vector 1, 0, negative 1, which if we were to turn back into P2 would be 1x squared plus 0x minus 1. And you can quickly check that this is in fact, in using our inner product, orthogonal to this guy and to that guy. For number 4 here, we want to create a 2 by 2 matrix A, B, C, D, such that when I do the inner product, I get 0. This would tell me I have one equation and 4 unknowns, so I'd have 3 parameters, 3 things I could choose. I just happen to notice that 2 times 2 would be 4, and 4 times 1, or sorry, negative 2 times 2 would be negative 4, and 4 times 1 would be 4. So if I make these guys be 0, this will definitely be orthogonal to my U matrix right there. So we'll pause there and pick up on our next video.